We're going to focus on tree-network problems because both the p-median problem as well as the p-center problem admits a polynomial time solution on tree networks due to the special structure. The p-median problem, there's a complicated algorithm for that, which I'm going to cover after we cover the stuff on p-center problem. But this is, I think, easier to absorb than the p-median algorithm. So let's just focus on this first. So we're talking about minimizing, again, the f function subject to dxvi being less than or equal to r over wi, with x being a subset of some tree network T, and x will have p points in it. Okay? So, this formulation, we've already talked about this. F of x is simply the maximum weighted distance of each vertex to a closest element of the point set x. Okay. Equivalent problem is to minimize this doesn't make sense. It should be this way. Sorry about this. Minimize r, subject to that. The original version of the problem. I guess after lecturing for 2 hours, I guess I'm a little out of synchronization with this stuff. So the original problem is to minimize f of x, x in t with x, cardinality of x equals p, where f of x is the maximum weighted distance. So the above problem is a slightly different version of the original problem, which is this one, the combinatorial statement of the problem. Now, I'm not going to use the add-ons, but you can certainly extend the ideas to the case with add-ons, but let's not worry about that right now. In solving this problem, again, we have a finite dominating set property. What's the finite dominating set property? We may solve a finite sequence of covering problems. To obtain a p-center solution. So let's call Rp to be the best value for the original problem. Likewise, Rp is the smallest value you would get here. Okay. We may solve a finite sequence of covering problems to obtain a solution x star with objective value Rp to a p-center problem. In the covering problem, we try to minimize, again, the cardinality of x subject to dx vi less than or equal to r over wi. X is a subset of T, no cardinality restriction, And the output of this is, say, some integer q as dependent on r, q of r. Just to refresh your memory, what kind of an r am I looking for? You're looking for a particular value of r, say r star, such that the output of the covering problem is less than or equal to, okay, less than or equal to the fixed number p, while q of r star minus epsilon is greater than p for any epsilon positive. So as soon as you reduce the radius a little bit, it does not admit a feasible solution with less than p points. Okay? All right. Now, first of all, of course, we're looking for r star, which is going to be also rp, if you can find it, okay? And it's quite obvious that the search can be confined to a finite set of numbers defined in this way. Bij, which is defined by the distance between I and j divided by the sum of the reciprocal weights. Why do I conclude that? Because in the one-center solution for three networks, the objective value happened to be how much? The largest of these numbers. Does everybody remember that? In the single center case, I call these numbers alpha ij's, so maybe that's why you don't quite remember, but I just call them bij's now. It doesn't really matter. They're a priori computable numbers, and the largest of them supplies a solution. In fact, when you compute the largest one, well, first of all, it tells you what the optimal objective value must be. Number two, whoever or whichever pair of indices realizes the maximum, that pair is a critical pair. And using that critical pair, you can actually readily locate the optimal one-center solution along the path between them. Okay? So if BST is the maximum such ratio, then the absolute one-center solution is a unique solution. It lies on the path connecting the pair Vs and Vt, where x star is such that the weighted distance between x star and Vs is equal to the weighted distance between x star and Vt, which is equal to Vst. This is something from before that we have already covered. So in the case p greater than 1, this actually still allows us to conclude that the optimal RP should be one of these numbers. Why is that true? Because again, if you have an optimal p-center solution, you can decompose the vertex set into p subsets, and then for each subset you can solve a single center problem using only the weights for that vertex subset and making all the other weights 0 for that subproblem. And then once you get one-center solutions of this kind for p times for each vertex subset, you can put them together, and that's going to give you a p-center solution. But the one-center solutions will be one of these numbers. Why? Because you're looking at a particular vertex subset, and of course, whatever the largest Bij value relative to that subset is, that will become your one-center optimal value for that subset. Okay? So I'm just rewriting what we already mentioned in words. We may decompose the vertex set into subsets where the ith subset has those vertices whose closest center in the set x bar is defined by xi bar. Okay? With that, we have f of x bar equaling maximum wi dx bar vi. This is overall vertices, which can be decomposed into subsets going from 1 to p. And for each subset, you maximize wj dx I vj. There's a bar here. Don't forget that. So I have P. I'm just decomposing this in such a way that for the ith subset, the closest distance between any vertex Vj in that subset is defined by the ith center. Okay? So this part is equal to the capital 1. And we do this repeatedly, or we do this separately for each I going from 1 to p. And once you do that, this part can be solved as a single center problem. So if you minimize this maximum weighted distance over all points x in other words, we're solving this problem, minimize x in t of maximum wi dx vi in, vj, let's make this j, vj in vi. Okay? So when you solve this, you get some solution, say xi star, or you get an x star and you name it as xi star. Okay? And when you replace xi bars with xi stars, since the maximum here is certainly less than or equal to the maximum in the upper one, because xi star is a minimizing solution to this, whereas xi bar is some solution, not necessarily optimal. You would have this. Sorry, greater, the other way around, like that. Okay? And this is certainly greater or equal the maximum of w j d x star vj over all j. Does everybody agree with that? Yeah. If you replace each small d with capital D, you can only get better, or you can only get smaller. So, and once you do that, of course, you don't need to have this in partitioned form, but you can just collect it into a single max operator, which is what we have done here. Okay? And that happens to be your f of x star. So you just showed that f of x star is less than or equal to f of x bar, which means, of course, x star is also optimal. Okay? All right, so all we did is we're trying to justify that statement, since there's always a p-center solution, which actually can be also modified in such a way that each center is the one-center solution of some subnetwork, then this statement must be true. Okay? In the absence of any add-ons, you don't need any I equals j case here, because in that case bij will be 0. So for that reason, you can put this into an ordered list from smallest to the largest in, say, non-decreasing order, and do a binary search and solve a covering problem for each choice of R from this list. During the search. Okay? You don't necessarily choose all bij's, but rather you choose only a subset of them as you go along. Okay. So the question that remains is, how do I actually solve the covering problem? Because once you know how to solve the covering problem, things will be quite straightforward as far as getting the p-center solution. Okay? Now, in the general network case, how you solve the covering problem, we resolved that question by actually solving a set covering problem by using the appropriate Aij coefficients in the matrix of coefficients. Here we can do much better. We can actually solve the covering problem in polynomial time because the tree structure permits you to do that. I'm going to give you an algorithm for doing that, but first let me apply the main ideas of the algorithm on an example problem. I'm going to term the algorithm cover, because it actually covers stuff. This is an example application of that algorithm. Here's my tree. Okay, I decided to use Z1 rather than R1 because I don't want you to confuse the RP values with the numbers that I use here. The Z1 is 12. It's some fixed number R divided by W1. I don't need to specify what the W is here because all we have to do is we want to solve that problem where these are the numbers. So the problem we're trying to solve is minimize the cardinality of x subject to distance between x and each vi is less or equal to zi, I going from 1 to 6, with x being a point set in T. That's what we're trying to solve. Okay? Zi are given upper bounds on the closest distances. Okay. Now, the algorithm does the following. It takes these numbers as upper bounds. And since you're looking for a point set x for which the closest distance between vi and the point set is no more than zi, that means there must be at least one element of the set x here within a distance of zi. And this idea of using strings works fine here. Okay? So what we do is we attach, for example, a string of length 12 to this one. And as long as you pull that tight towards other parts of the tree network, as long as that string covers, you should have at least one point x within the coverage of that particular string. Okay? So let's just do this. Except that, of course, you must know how to pull these strings in a systematic way to not get confused. Okay? That's the main idea. So the second one, Z2 is 7.2. So these wiggly lines are strings. If you can make them maybe in a different color, that probably works better. Z3 is 7. Number 4 is, how much is that? 6. This one is 18. And this one is 8. Okay? So these are my strings. John seems to like this idea. Huh? Okay, so let's begin by choosing that particular one. Why did I choose that one? Well, actually, I'd rather choose some tip vertex, a vertex of degree 1, and start moving from tip vertices, or some people call them leaves, from leaves towards the center of the tree, except that the center of the tree is not so well defined. Nevertheless, tips are well defined. So let's pick a tip, that one. Once you pick that, all you have to do is you pull that string tight towards the adjacent vertex. In this case, when you pull it tight, it actually has a length larger than the edge length, so it will go all the way, and there will be a loose end here of 4 units for the next iteration. So what we do is we do that. I'm going to draw the network again, tree network again. And because that one actually is pulled tight and reaches all the way, I am coloring that portion of the tree brown now. Brown tree is, or brown subtrees are dead subtrees. You don't have to do anything with them. But the live tree, the green tree, is what you work with. Okay? So initially, the entire tree is the green tree. And now this part has become the brown tree, brown subtree. So you remove that from the green tree. And you've got two string ends here. One is of length 7.2, the other one of length 4, because 12 minus 8 is 4. Okay? The other ones continue to remain on the tree. Next, I choose another tip vertex. In this case, I happen to choose this one. So the ones I circle, that's the one I choose for the new iteration. Now, the length of this guy is 25. So when I pull this particular string tight towards the other one, it will not reach. Okay? And when you do that, of course, it reaches all the way up to here. You have to have something here, at least one point. You can have something either here or there or anything in between, but because you want to be somehow able to cover the other ones as well, it's much better to actually locate it at the very end, okay, where the end of the string reaches. So in this case, in the next iteration, you're going to see the following. This part is already brown. There will be a new part that's brown here, whose length is 7. There will be an x1, which is located here. The remaining portion has a length of 18. And what else? As soon as I locate a new point here, I can also check the other strings. Does any of these strings reach that point, x1? Nothing? So there's nothing to do. Okay. So at this point, if some string had reached, I would have assigned that string to that particular x1, meaning that wherever that string originates at whatever vertex, that vertex is already covered by x1. But there's no such thing for this particular case. So all the other strings continue to. This one was what, 8? Okay. And I've got 7.2 and 4. All right. Now I choose again a tip vertex of the current green tree. The current green tree is everything except these cross-hatched parts. Okay? I happen to choose that one. That's something probably that you would not think of doing. Nevertheless, why not do it? Because I'm trying to actually shrink the green tree as much as possible while locating centers as necessary as we go along. Now, once you choose this, actually, there's no string attached here, so you just color that brown. Okay? So in the next iteration, we're going to have the tree with another part browned. It's this part, because there's no string there. There was no string at x1, so you just truncate it there. Okay? Of course, some of you may think that I could have pulled these strings tight towards here, but I don't have to. I can brown this and I can pull them actually towards the other vertices for the benefit of possibly covering other vertices as well. If you go this way, then you're getting away from other vertices. Does that make sense to everybody? Okay. All right. Right now, this is just some heuristic idea. It may look like a heuristic idea. Nevertheless, later on, we're going to prove that this actually finds the optimal solution to the covering problem. And proving that is, well, that's something you should start thinking about, okay? Why does this work optimally? All right. At this point, I've got my strings. This was 6. This was, how much, 8? How much was this, 18? Okay. That's the new situation. Let me see what I chose now. Well, I happen to choose this one. Was this V3 or V2? What was it? V2. I choose that. And pull these strings tight towards here, which means in the next iteration, we have another center located, say x2, whose the little portion here is 4 units in length, because the shortest string can reach only that much. Okay? This one covers all those vertices for which these strings originate at. Okay? All right. Does it cover any other vertices? How much is this? 22. So this is now 18 units in length. And the other ones, unfortunately, don't reach. So they survive. If one of them had reached, I would have just dropped that string by declaring that that vertex is already coverable by this point. Okay? But that did not happen. All right, next, what do you choose? Well, I happen to choose this one. What was it? V6? V6, yes. I could have also chosen that one, but nevertheless, that one is the one I chose. When you do this, the length here is 10, so it will not reach the next one. So in the next solution, we're going to get the following. As soon as you locate this guy, there's a length of 2 units here. There's a length of how much? 20 units here. So this one cannot reach, but that one reaches here. So I drop that. Okay, that string attached or engaged here with a length of 6 is already processed as soon as I located this guy. Okay, so it's deleted from the from further processing. At this point, we choose another one, which is V5. and you locate x4. This one has a length of 18 here. This is 2. This is also 2. This is 18. This one is 4. This one is, how much was this? 7. How much was this one? 25 minus 7, 18. This was 8 here. So the final situation is like this. All the strings are dropped, and so I'm already done. Yes?
I want to ask, can we locate x1 right at v3? Because
x1 right at v3. We could have done that probably, but I would not have known that a priori. After I get the solution, I might be able to actually relocate it if necessary.
Because x1 does not gives any service to any
True,
other
true.
ST, so it could be right at the v3.
True. Mm-hmm. Yes, actually, the answer is yes. When you located x1 at the very beginning, you checked for the remaining strings in the elsewhere in the tree, but none of them reached here. So you had a choice of locating it actually anywhere along this little segment. Nevertheless, I did not do that because the algorithm is not looking for actually alternate optimal solutions, but rather it's giving you a polynomial time method of constructing a solution to the covering problem. Of course, you should prove that. Okay. The idea here is when you write an efficient algorithm or something that you claim is polynomial, my advice is try to make it as lean as possible. Don't look for too many things. Look for only whatever you're trying to do. In this case, you're trying to solve the problem polynomially. Once you write it down in the leanest or cleanest possible way, so that you can prove it without obscuring with other details, then make it efficient. Okay? Because I know that many students try to make it efficient as well as make it work, but then trying to prove something that's cluttered with all kinds of details because in the interest of making it efficient makes it very difficult or sometimes impossible to prove. Okay? So you should always be somewhat, strategically, you should always try to first get provable stuff and then make it much more efficient. Now, that comment has nothing to do with the question you asked for. Nevertheless, let's just concentrate on the provable portion of this, and then we can discuss perhaps making it more. First of all, before proving it, wow, we have not much time left. Why is this algorithm polynomial? Assuming that it works. Meaning that it actually places the optimal number of facilities given the upper bounds.
Because we are looking at finite number of chips at the beginning, and then we are looking finite number of strings.
That's not enough.
What we are doing is requires a constant number of operations. First, we are looking for a T vertex, which is constant time, and then we are looking for strings that actually we are looking for vertices that force the cover algorithm to place a center.
Okay.
That forces, and we choose those vertices as P centers. So this is also a constant time.
Well, let me put it this way. I understand. When you have an algorithm, you need to analyze in how many steps you actually perform the entire job. Okay? Now, there's usually a main step which you keep repeating. The main step in our algorithm consists of choosing a tip. We're not really looking for a tip. We choose a tip because once you define the structure of the algorithm of the tree at the beginning, you know which ones are tips, which ones are not tips. Those with degree 1, by pre-processing, you can just put them in a list of tips. And during the progress of the algorithm, some additional points are placed, so they also are added as possible tips to that list. So, number 1, the main step consists of choosing a tip. Once you choose a tip, you actually pull a bunch of strings engaged at that, and you can always keep track of how many strings are attached and which one is shortest. So that is really not difficult when you want to make this numerically. And once you locate something, such as x1 or whatever, you need to check other strings whether or not they reach. Can all these be done in polynomial time per cycle, per repetition of the main step? Yes. We don't know how much, but it can certainly be done in polynomial time. So the next question is, how many times can I repeat in the worst case, can I repeat the main step?
N minus 1 times.
Okay, n minus 1, n squared, n.
When we actually do it n times.
No, I don't want any justification. Let me get the opinions first.
The steps are different.
How many times do you think I would repeat the main step in the worst possible case? Think and answer. I won't let you go otherwise. Huh?
N.
Okay, he says n. How many other people say n? Okay. You said n minus 1, you said n squared. You need to, perhaps, if you need to revise, let me know. Can it be more than n?
Yes.
Yes. Since I'm asking the question, it better be yes, yes. Why do you think it? How much? How many?
I looked at the example.
Uh-huh.
There are 7 iterations and 6. So yes.
See? Okay. It can be more than n.
Up to n maybe, because
Ah.
when we repeat the iteration and if we place an x1 and if we can't reach, then we put the remaining part in the brown tree, so maybe it is bound with 2n.
Yeah, 2n is a more reasonable bound.
But since there cannot be n tips, maybe 2n minus 1, because maximum number of tips.
Well, yeah, you don't have to be that exact. That's okay, yeah. But as in the order of still n, even if it's 2n, it could be more than n though, because you're locating some new points, and the new points will be at most how many? Well, if I'm covering n vertices, they cannot be more than n, okay? That's the worst. So 2n is certainly a good upper bound. It can be less than that also. Next time, well, I'm going to let you know, let you go. But next time, let's see if you can actually prove why you cannot have less than 4 points here and still cover everybody, every vertex within the given upper bounds. If you can construct an example proof, then we'll of course look at the general case.